rugged, and they have special error control protocols such that they won't time out in a RAID array. So if you are using drives in an array, you absolutely need the RAID ready, so-called RAID ready enterprise class drives. But even if you're not, I highly recommend them. I don't know what's going on. I mean, I had hard drives lasting years with no problem for many years, but over the last 5 years, I've seen just a large number of drive failures. I think drives have become such a commodity, the prices have become so low that we're just seeing, you know, the manufacturing processes are a little bit less, well, they're less expensive. So to fight that, I buy enterprise class drives. Now, this is especially important if you're dealing with external drives. Now, a lot of people will go to the store and buy an external, you know, USB or FireWire or even eSATA drive. And what they're getting is a drive enclosure, you know, like this. And in that enclosure comes a hard drive. Well, you're never going to get a RAID class or enterprise class highly reliable drive in a pre-built enclosure. So what I recommend is buy your own enclosure. This one costs $30, and then I buy my own, you know, RAID class, enterprise class drive, and I simply build my own. It doesn't cost me, in fact, it generally costs me less than the pre-assembled store-bought enclosure with the drive already installed. Now, another thing you can take advantage of with the serial ATA drives is eSATA. That's E for external serial ATA. Now, you can, in fact, many motherboards will come with this. This is a SATA to eSATA bracket and cable assembly. So this connector here plugs into the SATA connector on the motherboard, and then it presents an eSATA connector on the back of the PC. Now, eSATA connectors are different from SATA connectors. I mean, this connector will not plug in here. This connector is designed for internal use only. This connector is designed for external use. So if I have an eSATA capable drive enclosure like this one, what I will want is an eSATA cable like this one here, which I can then plug into this connector that provides a reliable connection that's designed for external use, and then this will plug into the drive. The advantage of eSATA, you can have that same high-speed connection that you have internally with an external drive. This is 2, 3, or more times faster than USB. So if you use external drives a lot for backup, you deal with large files, and you want the fastest transfer rate, go eSATA. Now, here's one disappointing thing. Virtually all of the external enclosures that support eSATA only do so at the 1.5 gigabit per second rate. So even if you have a 3 gigabit per second drive like this one, it's only going to work at 1.5 gigabits per second via eSATA. Now here's where knowing about that jumper may come in handy, because if you build it and it doesn't work, you may have to install the limiting jumper depending upon what type of circuit board is in the particular enclosure that you're using. Now, if you deal with a lot of external drives, you want multiple eSATA, you can actually get brackets like this one here that have 2 eSATA ports on them. So that's something to consider. And that way I could run multiple enclosures and copy from drive to drive and things like that at virtually the same speed as having the drives internally mounted in the system. So I hope these tips will help you, build, both buy more reliable drives, connect them up properly, make sure that they work, and even if necessary, build yourself your own more reliable external enclosure. In this segment, we're going to talk about motherboards and take a detailed tour of a modern motherboard in a system. Now, when you're buying or building a system, the motherboard is the main platform into which the processor is plugged into, the memory, all your expansion cards, etc. So in many cases, it's really the most important part of the system. I know a lot of people think of the processor as the most important, but the motherboard is what the processor itself plugs into. Now, normally when you're putting together a system, buying or building, you're going to decide, oh, I want this certain type of processor. Then that gives you a range of chipsets to consider. See, the main circuitry on the motherboard is what we call the chipset. Now, modern motherboard chipsets normally consist of 2 chips, what we call the north bridge and south bridge. I have a diagram here showing a typical motherboard block diagram, and the north bridge and the south bridge are these components here. The processor would be in the socket represented by this top portion of the diagram. So when, let's say you want to build a system with a Core i-Series processor from Intel. Well, you'll have to look at what chipsets support the specific processors that you wish to select. Then you need to examine only motherboards with those chipsets. Let's say you want to build an AMD Phenom 2-based system. Again, you need to find out what chipsets support that processor, and then you can then narrow down the choice of specific motherboards from the motherboards that support that processor. Now, one of the other big choices to make in a motherboard is the form factor. The motherboard I have here right now is what we call a full-size ATX form factor. That is traditionally the most common. It's been in use since 1996, by far the most popular form factor. So if you're building a system with a full-size ATX motherboard, you have just hundreds, if not thousands, of different types of cases to choose from that will fit this board. Another choice you can make is what's called a micro ATX board. This is an example of a micro ATX board, and as you can see, it's basically a subset of the full-size ATX. I mean, it actually has a subset of the screw holes and of the dimensions. So if a case would fit this big board, it will automatically fit this smaller micro ATX board. Now, if you are building a system using a micro ATX board, you can buy a smaller case that will fit just the micro ATX board. Obviously, then the full-size board wouldn't fit in that. So that's another consideration. Generally, with the micro ATX motherboards, you have fewer slots, fewer expansion ports, and fewer features in most cases. However, there are some very fully featured, fully loaded, I should say, micro ATX boards. So now, let's take a look at this particular board in more detail. Now, as I said before, we have the socket that the processor plugs into. Then we have what's called the North Bridge and the South Bridge component that are part of the motherboard chipset. Let's see where those are physically on this board. Well, this motherboard is what we call an LGA 1366 socket, and that is right here. Now, the LGA 1366 stands for Land Grid Array 1,366 pins. Now, land grid array means that the pins are actually in this socket. And that's why you'll notice this particular one still has the protective cover on it, which comes from the manufacturer, to prevent you from accidentally damaging any of the pins here. See, the little pins are sticking up from inside the socket. And if you were to touch them with your finger or snag them with a piece of cloth, you'd bend them and possibly render the motherboard inoperable. The processor itself doesn't have any of the pins. It just has lands. It just has basically gold spots that make contact with the pins when it's inserted. So you'll see these protective covers. And I recommend not removing this cover until you're ready to directly install the processor. The North Bridge component is right here in this case. Now, North Bridge chips in modern systems tend to run hot, so in most cases you will find some sort of a heat sink on them, as you see here. Now, this heat sink is a fairly advanced heat sink. It has what's called a heat pipe that helps distribute heat among voltage regulators here. This is voltage regulator circuitry for the processor. It basically provides power to the processor. Then we have the heat pipe connected again to the North Bridge, and then over here to the South Bridge. This is the South Bridge component, also under a heat sink in many modern motherboards. Now, in newer processor designs, what we found is that the both Intel and AMD in their most recent processors have moved the memory controller from the North Bridge, this is where it used to be, into the processor. So in this block diagram you can see I have memory modules that will be attached directly to the processor. The data flows between the processor and memory directly. It doesn't have to go through any other chips. And this particular design with the LGA 1366 uses 3-channel memory. So in other words, the processor can talk to 3 memory modules at a time. Now let's find that on the board here. Here we see the memory sockets, and we have 6 of them. So that means we have 2 separate sets of channels. We have 3 white sockets. That represents the first channel. So when I buy my first 3 memory modules, I'll plug them into those 3 white sockets. Then the 3 light blue sockets are the second channel. And when I buy more modules, I'll plug them in there. Now, for maximum performance, being this supports 3-channel operation, you'll want to install memory modules in groups of 3 at a time. And all 3 should be the same capacity and the same speed, and ideally from the same manufacturer. So I recommend, in other words, buying them all at the same time. Now, you can run this in dual channel operation or even single channel. In other words, it's possible to run this motherboard with just 1 memory module in it, but you will lose some performance if you do that. Now, according to this diagram, you'll see that on the north bridge component, we have a connection to the video card slots. These are PCI Express by 16 slots, and we can see those here. These 3 long slots, 2 blue ones and one sort of an orangish colored one. Why are they different colored? Well, the 2 blue ones support X16 operation. That means 16 lanes of connection. And both of those can be used at the same time. Now, the orange-colored one here only supports 8-lane operation. So while you can use 3 video cards in this particular motherboard, the third one won't have the same performance. It'll have half the throughput of the other 2. So that's a limitation of the chipset. Now, what else do we have? Well, that's the only other connection from the north bridge. So the north bridge connects to the processor, it connects to the video, and then it connects to the south bridge. Now, this north bridge to processor connection is called QPI from Intel. That's Quick Path Interconnect. And that supports a very high performance bandwidth of over 25 gigabyte per second transfer rate. So that's an extremely high performance connection between this north bridge and the processor. Now let's look at the south bridge. The south bridge is a very much, how should I say, overworked or in-demand chip in a modern system. As you can see, look at all of the interconnects to the south bridge. For example, in this we have the audio. And on this motherboard, we have audio chip, which is actually located right here. So this chip right here provides a connection to the audio jacks on the back where you can plug in speakers. This one happens to support 7.1 audio, and this happens to be a Realtek audio chip. What else do we have in here? We also have gigabit Ethernet right here, represented by these 2 blocks here. The gigabit Ethernet chip is located right here, and that provides a connection to the Ethernet port on the back of the motherboard here. So there's the Ethernet chip. What else do we have? Well, a big portion of this is the interface to hard drives, and what we have is 6 serial ATA ports made possible by this particular south bridge. This one happens to be called the Intel ICH-10R. That's I/O Controller Hub 10R for RAID edition. And we find those ports right here. There are 2, 4, 6 serial ATA ports that are connected to this south bridge. Now, on this motherboard, there happens to be 8 hard drive connectors. There's 2 more serial ATA ports here. Well, where did those come from? Well, that's from an auxiliary chip. See, some motherboards manufacturers will put accessory chips in there in addition to the chipset to provide additional functions. Kind of like, we mentioned the audio and the Ethernet. Well, this particular motherboard has a second serial ATA controller right here, which powers these 2 connections here. So we have additional connections for serial ATA. We can run up to 8 hard drives on this board. Okay, what else do we have? Well, if I look over at the diagram here, we also have a connection from the south bridge to up to 6 PCI Express by 1 connectors. Now, we don't have 6 PCI Express by 1 connectors on the board, but we have, here's a by 1 and a by 4 connector. Also, we have an interface to standard PCI. That's also built into that south bridge. These are for older, just standard PCI cards, not the PCI Express. Now, what else do we have in a board like this? Well, this board happens to have, a lot of additional features. It has, for example, over here, a built-in power switch and a reset switch. This board is kind of designed for overclockers, and when you're overclocking a system, you might get into a place where it locks up, and with the system open and having easy access to a power and reset button is something that they thought was desirable here. How about power connections? There are several power connections that are used in a modern motherboard. We have the main ATX connector here, which is a 24-pin connector. That's the main connection between the power supply and the motherboard. We also have an 8-pin CPU power connector here. This connector basically powers the voltage regulators, which then provide power to the processor. So those are the main connections between the motherboard and the power supply. Now, what else do we have on this board? Well, there's also fan connections. You'll see interspersed throughout this board several 3- and 4-wire fan connectors. This board has quite a few of them because it supports running not only the processor fan, but a rear case fan, a front case fan, and even other auxiliary fans. Typically, you'll find at least 2 or 3 fan connectors on most boards. Some high-performance boards like this one will have even more. This board has additional functions as well. Built into the south bridge are also USB ports, 12 in fact on this particular chip. So we have 8 USB on the back, and we have 2 USB headers here. These are designed for front panel USB ports. Each of these supports 2 more. Each of these headers supports 2 more ports. So you could have up to 4 front panel USB ports, and the cables for those would plug into these 2 headers here. We also have headers for 2 FireWire ports, and there's an additional FireWire port on the back of this board, and that's all supported by a Texas Instruments FireWire chip, which is located right here. So this provides 3 FireWire ports, 2 that you can optionally run to the front, 1 built in for the back. Finally, I wanted to mention here, over here is the connector for the front panel audio. In other words, if your case has jacks for a microphone and headphones and things on the front, you'll plug the cable from the case into this connector here. So that's an important connector to know about. So those are the main points that we see on this motherboard. You'll find that many modern motherboards have similar sets of connectors. And if you want to know exactly where things are located on your motherboard, I recommend you check the manual. I find that today, most motherboard manufacturers are really good about giving detailed diagrams showing where all the connectors are and what they're used for. In this segment, we're going to talk about memory types and technologies from the very first PC to the present. Now, having been involved with PCs since the very first one came out, I've seen memory change tremendously over the years, and I thought it'd be interesting to take a look at all the different types of memory that we've had available, and in some cases to see, the physical, how it appeared, what it cost, and that sort of thing. Now, going back to 1981, when the very first IBM PC came out, you didn't have very many choices when it came to buying memory for the system. And initially, you had this choice right here. This was a 64K memory card that was available from IBM, 64 kilobytes of memory. And at the time, this cost a whopping $540. See, back then, 9 16K chips, which is what it took to make up 16K, cost $100. And this actually has 36 chips on it. They're double stacked. There's two sets of chips from what you see here. So there's $400 in just these chips alone. And these chips ran 200 nanoseconds, which is about 5 megahertz in speed, which of course matched the speed of the PC at the time. Then, a year later, we had this card become available. This was a 64/256K card. This could hold 4 times the amount of memory as the first card here. And what we had was, this would have banks of 64K chips. We had 1, 2, 3, and then 4 banks of chips here. Normally, this card was sold with just 64K on it, and then you would manually add the rest of the chips. Back then, what we had to do was buy chips. They usually were sold in these little tube-like containers, and you would take the individual chips out of the container, like this. This is one of the memory chips. We'd load it into a memory insertion tool, like this, and then you would use this tool and put it over the socket, and then press down and push the chip into the socket using this tool. As you can imagine, it would take quite some time. I remember spending hours filling boards like this. I mean, look at the number of chips on this board. Think of how long that would take to make sure you got each one in. You had to have each one properly oriented, not miss any of the holes. And if you did, boy, you had all kinds of troubleshooting to go through. Well, okay, so we went from 1981 to 82. Then over here, I'm jumping up to 1985 with this card. This card came out after the IBM AT came out, and at the time, this card cost a whopping $475. Now, the good thing was that this card had up to 2 megabytes of memory on it. So we went from 64K to 256K to 2 megabytes. And for the 2 megabytes, of course, when you consider it was still about $500, the price per K had come down quite a bit. Now, after 1985, that was when we started to get away from memory cards. if you look at these cards, you'll note that they actually plugged into bus slots on the motherboard. Back then, the motherboards had very limited memory expansion, and when you wanted to add memory, you had to buy a memory card. The problem with these memory cards is that they were limited to the speed of the bus in the system. And oftentimes, even though the processor and other components on the motherboard were running faster and faster, the memory or the bus slots had to stay the same speed because cards had to be designed to work with them. So this was a very limiting in terms of performance. Well, in 1986, we had the first SIMs come out, and the first type were these 30-pin single inline memory modules. That's what SIM stands for. And the term single inline means that it's really one row of connectors here. You see a row of connectors on this side and a row of contacts on this side. Even though there are contacts on both sides, they are the same. They're redundant. Now, this particular 30-pin SIM holds 256K of memory. That's the same as this card here. So when you think about it, all of these chips are replaced by just 3 chips on this tiny little board. That was progress at the time. Well, from the 30-pin SIMs, we went to the 72-pin SIMs here. This is an example of a 72-pin SIM. This one happens to hold 8 megabytes. That's 4 times more than this entire card in just this little memory module. Now, back then, these modules ran at 5 megahertz for this. The board ran at 10, and these modules here ran up to 16 megahertz. That was the top speed available for memory at the time. Well, we had a breakthrough in memory when this type of module came out. This is known as a DIMM, and the type of memory that goes on this DIMM is called SDRAM, synchronous DRAM. And the synchronous was important because that meant it ran in sync with the motherboard. This stuff was available at speeds up to 133 megahertz, which matched the speeds of the motherboards and the chipsets at the time. Now, the SDRAM was popular between 1998 and 2002, and it replaced these 72-pin SIMs here. So from 1998 to 2002, we had a lot of systems using this SDRAM. Now, starting in 2002, that was replaced by something called DDR SDRAM. The DDR stands for double data rate, and just as the name suggests, it ran twice as fast as the single data rate. So these modules were different. They were not interchangeable, different set of contacts. And these were also DIMMs, being that the memory contacts were on both sides, and they were different. So now we had twice as many contacts without having to have the module be much longer. So this is the DDR DIMM. After DDR, we had DDR2. Now, DDR2 came out in 2005 and was popular all the way up until 2008, 2009. We're still using DDR2 today, but it's being replaced today by DDR3. Now, looking at the DDR2, that memory ran up to 1,066 megahertz. So that kept pace with the motherboards and chipsets at the time up until we needed something faster. So what happened was from DDR2, we go to DDR3 memory, and that's the current state-of-the-art that we're using today. DDR3 came out in 2008, but in late 2009 it started to become really popular, and that was when the price of the DDR3 equaled about the price of the DDR2. Now, when you look at prices of memory, it's pretty amazing. This DDR3 module that I have here costs only $40, and that's 2 gigabytes of RAM. 2 gigabytes for $40. I did some math, and putting that into 1981 terms, to buy that much memory in 1981 would cost over $8 million. That's how much the price of memory has come down. It's pretty amazing. So these days, if you're buying or building a PC, in most cases it's going to use DDR2 or DDR3 memory, with most likely the switchover is now happening very rapidly to DDR3. Now, let's take a look at a little bit, how this technology works. We mentioned that the double data rate, ran at twice the data rate of the single data rate modules. Now, DDR2 is not again is not like a quadruple data rate. What they did there was they added extra signal pins in order to improve integrity. So the clock could go higher. We could go up to 1,066 megahertz. With the DDR3, we're up to 1,600 megahertz with these. And in the future, they may even go faster. So most of the modern motherboards today will use DDR3. That's with the Core i series from Intel and the Phenom processors from AMD. Now, when you're installing memory, probably the biggest thing you have to look out for is plugging the memory in either backwards or not fully inserted into the slot. And I wanted to point out, here I have an example of a memory module that I took out of a system. And if you look here, I can see two pins where the gold has actually been literally burned off the module. That's because the person who installed these either didn't ensure that they were fully seated, fully inserted into the socket, or they plugged them in backwards. Now, to prevent plugging in backwards, you'll find keying in the form of a notch on the module, which must match the notch on the socket. Now, sometimes this can be confusing. For example, in the case of the DDR2 and the DDR3, they both have the same number of pins. They're both 240 pins. So, yet they're incompatible with each other. How do you make sure that the right memory goes into the right socket and in the right orientation? Well, if you notice, the notches on the DDR2 and the DDR3 are in different positions. So by altering the position of these notches, these keyways, they try to make sure that you can't plug it in backwards. But even with notches like this, I still come across burnt memory pins fairly frequently when people try to install memory and they don't know exactly what they're doing. So in any case, when you are installing memory, take care to make sure it's fully inserted in the socket and that it's in the right orientation. Well, I hope you've enjoyed this look at PC memory types and technologies throughout the years. In this segment, I wanted to talk about the latest processors and chipsets and kind of what's going on with these components. What are the latest advancements and features? Now, when we talk about processor, everybody knows what that is. That's the brains of the system. What do we mean when we say chipset? Well, the chipset is the circuitry on the motherboard that interconnects the processor to everything else. It's kind of like, I think of it as the central nervous system, the spinal column. It carries the data to and from the processor and to every other component in the system. Now, traditionally, the way systems have been designed, we had the processor and a two-chip chipset. Shown in this diagram here, the processor's on the top, and the two-chip chipset is here with what we call the north bridge, or memory controller hub, and the south bridge, or I/O controller hub. And, like the names imply, the memory controller hub typically or traditionally had the connection to memory. So in other words, the memory modules would be connected to this middle chip here. And then the problem with, I don't know if it's a problem, but that design means that any data that would go to and from memory had to go from the processor to the memory controller and then out to the memory modules. Well, AMD in 2003 with the Athlon 64, in addition to originating 64-bit technology, they also originated something that was sort of revolutionary. They moved the memory controller from the north bridge into the processor. So now, instead of connecting the memory modules to the north bridge and then having that data have to travel to the processor, now it's connected to the processor directly. Intel has recently also adopted this architecture in the Core i series processors. So the Core i series now in 2008 also have the memory controller built in. Now some people would say, well, geez, AMD had that in 2003. Why did Intel take so long? Weren't they at a disadvantage? Well, you might think so, but not actually. See, the real deal is that when a processor accesses memory, it only needs to talk directly to the memory like about 1% of the time of operation. That's because of what we call the cache, the level 1 and level 2 cache that was built into the processors. Now, in another segment, I talked about processor technology and how the cache originally had been on the motherboard and then was moved into the processor, built right into the processor die. That was true with level 1. The first processor to have level 1 cache was the 486 processor. Level 2, that was the Pentium Pro or 686, which then became known as the Pentium 2 and Pentium 3. Those processors had the level 1 and level 2 built in. Well, more recently, processors now have level 3 built in. That's kind of one of the new advancements. The latest AMD Phenom processors and the Intel Core i series processors have now 3 levels of cache built in. And because of this cache intercepting calls to memory, the fact that the memory controller was in a separate component wasn't that much of a disadvantage. Well, finally Intel has gotten on the same bandwagon as AMD with that. So in this example of a Core i series system with an LGA 1366 socket, we can see that the memory is now directly connected to the processor. And this example uses triple channel memory, which means 3 memory modules at a time simultaneously are being talked to. So we have extremely high bandwidth. A lot of data can flow there. Now, if this north bridge component, used to be where the memory controller was, and now that's been taken away, well, what else does it do? Well, it's also acting here as the interface to video. So when you plug, your video cards into the slots on the motherboard, they are connected now to this what's called an I/O hub, and then the data travels to and from the processor.